Alright, in these videos, we're going to be recording some videos in order to understand how we're going to be calculating the normal distribution and the z-score associated with it. Of course, there are some rules we need to understand before we do the z distribution, and also there is t distribution, proportion distribution, and the chi-square distribution. I'm going to go ahead and start by explaining or give a general idea about what each one of those, but we will remind each other about what is really required to accomplish one of those. If you notice with the z distribution, it's based on normal distribution, and the standard deviation of the population in this case is known. So this is a very good indication that z distribution must be used when the standard deviation of the population is known. And there is another requirement that I write down here: if the number of n, the number of the object or subjects rather, is going to be greater than or equal to 30. The t distribution, which is the student's test, if alpha actually, I'm reminding you here again, if sigma, is known, then we would use the normal distribution. What is sigma? Is the standard deviation for the population. If sigma is not known, then we're going to look at this one here. If the n is large, then we still use the normal distribution. However, if n is small, then we're going to use the t distribution. It will become clear from the nature of the problem when we understand what it's really giving and how we should be able to solve it. The p distribution, which is the proportion distribution, is very interesting because it will be based on the normal distribution if it does meet the two requirement, the number of the items multiplied by the probability, or the proportion, I'm sorry, is going to be greater than 5, and other requirement would be the number of n multiplied by q. Q is the what is left out of p if we subtracted from 1. So again, when we talk about flipping a coin, the probability of getting a hit is 0.5. So what would be the p is going to be 0.5, but what is q is going to be 1 minus 0.5, which is going to be also 0.5. Different from a die, which is, of course, it's 1/6 for each value in it. So in order to pass this test, we need to look at, let's say we have 50 items, or 50 subject here, or 50, the number of the sample is going to be 50. So n multiplied by p, if the sample size was 50 and the proportion is 30%, then it's going to be 40 multiplied by 0.3. It's going to be 15. That's past the first requirement, which is 15. And again, 50, which is the size of in the sample size of the n is the sample size basically. 1 minus 0.3 is going to be 50 multiplied by 0.7. That's 0.7 came from the fact that I subtracted 0.3 from 1 in order to get 35. So these are both larger than 5, so you can use the normal distribution with the proportion distribution. The chi-square distribution is one right tail. It's very interesting to know that the chi-square test is intended to test how likely it is that an observed distribution is due to a chance. Okay. Also, it's called goodness of fit statistics, chi-square distribution. It measures how well the observed distribution, we'll take that as an example in order to see how well is the observed distribution of data fit the distribution that is expected. So there's two types of calculation we have to go through. Observe is, of course, is given by the study itself, and expected we have to figure that out. Luckily now we could do that all by software, but still we're going to do everything is slowly. And after that, we're going to decide how to build all this knowledge that I discussed as we speak into hypothesis testing. So all hypothesis testing going to require 5 steps. First of all, to state the null hypothesis, which is the HO. It's going to be always based on equality. In this case, we're going to be talking about means. So it's going to be for example, let's say the mean, which is a mu, is going to be always going to be equal to some value. And so this value is, we're going to determine that through the study. And also the null hypothesis, which is going to be what if left out of the equality. Was left out of the equality after we test for the equality is going to be either not equal, not equal, greater than, or less than. So usually the alternative hypothesis, the null hypothesis is always have to be stated as equal. Then we're going to determine the alpha value, which is going to be normally is 0.1, like 10%, 0.05, 0.02, or even 0.01. If the alpha is 0.1, then that C, what do you call it, the confidence level, or the C value confidence level is going to be 1 minus the alpha. So it's going to be 1 minus 0.1 is going to be 90%, for example, the confidence for the first alpha. The second one is going to be 95%, it's going to be 98%, then it's going to be 99%. After we determine the level of the confidence, then we'll be able to look at the critical region, the critical region value. For example, we know we have to determine whether it's one tail or two tails. Based on not equality, always we're going to end up with two tails, which means we're going to divide the value of alpha by 2. And less than is going to be left hand, and greater than is going to be right hand, and it's going to be 1 alpha value. So we're going to be looking either at the back of our book in a table to find the Z or the T or the chi or the proportion critical value, and as a result we'll be able to see what we obtain, or we're going to be able to directly access it by Minitab software in this case, which is much easier, as we will see in the next videos, actually in the next 4 videos. After we determine the critical region and the Z value, for example, I'm going to base this example on Z. If assuming like we have 95% confidence interval or confidence level, that's mean alpha is 0.05. And at that time, we're going to be able to say this is the Z-score. If one region, the Z-score, it's going to be, I could look it up very quickly by showing you directly how I'm going to do it. So I'm going to go ahead and enhance the recording region, so I'll be able to see, let me go ahead and get that here directly. This is my mini tab, and you will notice this is still Excel, so let me go ahead and do mini tab here. I hope it's coming here because I'm accessing it through another place through the, in 1 second, it should be here in a second. Maybe it's behind it. All right, 1 second. It's right here. Here we go. All right, so I'm going to be looking at this, and it's going slow here. So this is my mini tab. I could go to the graph. Let's assume that I have an alpha with a value that is based on the right hand. So I'm going to go to the probability distribution with the graph. I'm going to go to the view probability, click on OK. It's normal distribution. As you notice, always the mean is going to be 0. The standard deviation is going to be 1 in order to get that critical region value. The standard deviation, the probability is going to be 0.05. But we can also make sure it's the right tail. If it's left tail, it's going to be here. If it's actually both tail or middle, I use the middle always to cover both of them, but this is also a good way of looking at it, both of them. I'll actually run through an example in order to show you the difference. So these are the critical region when Z is going to be 1.960. This is for 2. My intention was to do 1, so I'm going to close this very quickly and correct my mistake. I'm going to do it one more time up in this one here on the actual, here we go, the right one, here we go. So the critical region is not 1.9, it's 1.645 because it's one tail and it's the right tail. So later we will see when we do the calculation for Z, that is going to be determined by all the given parameters based on the standard deviation and the number of samples, or the samples, yeah, the number in the samples. And we're going to be also looking for the calculated sample means. And also we need to be able to, of course, access the means for the population. And we'll be able to find the z-score, then we'll have to decide on where does that value fall. If it falls greater than 1.645, then we're going to be able to reject the null hypothesis. Finally, we're going to be able to state the decision based on any specific problem that is given. I hope this is make a little bit more sense, and we're going to continue with the next video where we're going to be looking at the disease distribution and also with some real example. Thank you.